In this video, we're going to look at evaluating piecewise defined functions and also writing piecewise defined functions from graphs. We're going to start with the evaluating part. So here I'm given f, which is defined as being three parts, three separate functions being put together around different values of x. And I want to start with finding what f of 1 is. So what you do is you go inside of f, and I'll go to look at the intervals. Where am I allowed to put 1? Well, this top part here, this top equation can only be used for x values that are less than 1. This middle equation says if x is greater than or equal to 1 or less than 3, I can use this middle equation. So that's the equation we're going to use. So we would take the 2 to the x power minus 1. You take 2, put in the 1 for x, and simply evaluate. So f of 1 for this piecewise defined function is just 1. And similar, we're going to do the same process again for f of 2. Well, f of 2 lies inside of this interval here, so I'm going to use the same equation all over again and say 2 to the second power minus 1 gives me 3. Now, let's look at the third one, which asks us what is f of 3. Well, I go into my piecewise defined function and I look and say, all right, well, this middle part here, x has to be smaller than 3, can't be equal. And the middle one here says you can only use it if x equals 3. So how do I get an answer for 3 for f? Well, you don't. It's not defined. You can say undefined or no solution, but it's not defined at 3, therefore it has no value. So let's do this process over again. So new piecewise defined function here. I want to find 3 values. So find what f of negative 3 is. Well, I look at this first piece, and this top equation, f to the negative x plus 2, I look at this inequality, and it says I can use this equation here on the left for all values of x that are less than or equal to negative 3. So I'm going to use the 2 to the negative x power plus 2. And I'm going to put negative 3 in there. So 2 to the negative 3 power plus 2, which is going to give me 2 to the third plus 2, which gives me 8 plus 2, 10. Now I want to go find f of 0. Well, 0 lies inside of this interval here between negative 3 and positive 2. Now, for this, we're going to use the function of 3, which means that no matter what the x value is between negative 3 and positive 2, you're going to get an output of 3. And lastly, f of 4. Well, 4 falls inside of this inequality of being greater than 2. So I simply would just go put the 4 where that x is. So I have the square root of 4 plus 5, which square root of 9 gives me 3. So that's evaluating piecewise defined functions. Now let's talk about how to write the equation of a piecewise function from a graph. And so what we do is we have to apply our function transformation rules to our parent functions to the best that we can. So I'm going to zoom in here. I'm going to look at these parts of this piecewise defined function. And I try to identify the functions, the equations they would be. And so I work my way from left to right. So this equation on the far left is a horizontal line at y equals negative 3. Now, if I was writing the equation, basically that would just be y equals negative 3. And I would have to trim the domain down, and we'll go back and we'll do that parts of the domain here in a minute. Now, let's go to the second function, which is here in orange. That function there is the square root of x. That's this parent function with some translations being applied to it. Now, I need to figure out what the starting point is for this square root function for when it comes time to start writing the equation. The way you determine the starting point is you look at the rates of changes between x's and y's. So I'm going to pick this point over here on the far right. If I go to the sideways one, my change is 1. Well, that doesn't really help me out a whole lot. But if I go sideways 1, 2, 3, 4, my change is 2. So that means I picked the correct starting point to use to base my transformations off. Notice that pattern would not have worked at that open circle, because if I went sideways 1, I only went up just a little bit, so that would not work there. Now let's go to the third function. I'm looking here at this third function. This is definitely the cubed root of x. It looks just like it. In fact, it wasn't even moved at all because that point of inflection is still right there at the origin. And the point of inflection is the point that we use for the cubed root function to identify the transformations off of. And lastly, down here in the far right corner of the screen, we have a parabola whose parent function is x squared. And we identify the transformations or translations of a parabola based on where the vertex is, because the vertex should have been at the origin. So we identified the parent functions in play. Now we're ready to write their equations. So a piecewise defined function, so some function of x, is going to equal the combination of all these pieces we have to put together to make this graph. And I work my way from left to right. Well, the first equation we have is y equals -3. We don't write y equals inside of the piecewise defined part that we're working on because f of x is technically y. So this first piece is just -3. Now, we have to write the domain in which we lie on that line, and so that represents the x values in which we are on this horizontal line at -3. The x values go from -9 to -5, and I'm going to use interval notation. Now, we have to figure out, do we use parentheses or brackets for the interval notation? Well, the open circle at -9 means that I have to exclude the -9, and the closed circle at -5 means that I have to include it. So I use a bracket. Now let's go to the next one. So the next parent function we have is the square root of x. So I'm going to go ahead and write the square root function. Now that point that we highlighted to base our transformations off of should have been at the origin. And so I moved that point to the left 1 unit. So that means I have to add 1 to the x inside parentheses. And I moved it up 4, so I know I'm going to have my equations start out like this. Now the square root function should have been going up and to the right and be concave down, but instead from the starting point it's going down to the left and it's concave up. So I actually flipped it over both the x and the y axis. Now the domain in which we're on this square root curve, open circle at -5 means parenthesis, closed circle at -1 means bracket. Now going on to the next function, which is the cubed root of x. Let me match my colors. The cubed root of x has the point of inflection still there at the origin. It wasn't moved sideways or up or down at all. It also was not reflected at all. So its equation is simply the cubed root of x. I just need to write the domain in which I was on it. Open circle at -1 means parenthesis at -1. Closed circle at 8 means bracket. And lastly is the squaring function, x squared. So I'm going to pre-make my parent function there with the squared on the outside. And we put x in because we're not doing any stretches or shrinks here. Now that vertex should have been at the origin. It is now at 9, -5. So I moved it to the right 9 units, which means I got to do x minus 9 for my transformation rules. And I moved it down 5 units, so I had to do -5. On the end. Now I also reflected it because the squaring function should be opening upwards, should make a U, but instead it's making an N. So there is my equation. Now I look at my endpoints here. I have solid endpoints on the end, so it would be a bracket on the 8 and a bracket on the 10. Leftmost point on the curve, the rightmost point on the curve. All right, let's look at another one here. So we're going to start off trying to write this piecewise defined function by trying to identify the parent functions first and the points that we base the transformations off of. So working from left to right, this first graph here in red is x to the third power. The point we base our transformations off of is the point of inflection, which is right there at -7. The next function we get to there in orange is the absolute value. Absolute value indicated, you get to see the pointed part, the elbow, and it looks like the V. In this case, it's just turned down. The next function we get to is the squaring function, so x squared, and we identify the transformations of x squared based on where the vertex is. Next one we get to, square root of x. Now, the square root of x, we got to find that point where we have a 1-to-1 change from the horizontal to vertical. If I start with the left point, if I go right 1 unit and up 1 unit, if I go right 1 unit from that point, I only go up just a little bit. And since we're not stretching or shrinking our graph at all, that can't be the starting point for the square root, which means that this other point here on the right-hand side is. Because if I go horizontal 1 unit, I go vertical 1 unit. If I go horizontal 4 units, I go vertical 2 units. So that's that change that we're looking at. And lastly, we have a horizontal line here on the very end, has a y value of 1, and so that's the equation that we would use for that. So now we're ready to piece all these things together. So when we piece together these piecewise functions, we start by writing f of x. And then we're going to put all these pieces in. So we start from left to right. Well, we have the first parent function was x to the third power. So I'm going to pre-make my parentheses. I got my function being raised to the third power. Now, x to the third is supposed to be an increasing function. This graph of x to the third is decreasing, which means I performed an x-axis reflection. I also moved that point of inflection to the left 7 units, so I need to add 7 to x. And I moved it up 1 unit, so I need to add 1 onto the end. The domain in which we're on this x cubed function, leftmost x to rightmost x value on this red graph, I go from -9, open circle, so parenthesis, to -5, close circle, so bracket. Then we go to the next function, which is the absolute value. I identify the transformations of the absolute value based on where the pointed area is, or the elbow. So I'm going to pre-make the absolute value, put x inside of it. Absolute value should open upward like a V does. This one opens downward, so I've reflected it. That V should have been at the origin, but it's not. It is at -2, 3. So I need to move it to the left 2 units, so I add 2, up 3 units, so +3. And now we do our domain interval. So the leftmost x value of this graph is at -5. The rightmost x value of this absolute value is at -1. So parenthesis, -5, bracket, -1, because one had an open circle, one had a closed circle. Now I'm looking at x squared. So I'm going to pre-make my squaring function. It's opened upward, so I don't need to reflect it. I'm going to put x here on the inside. The vertex was moved to the right 1 unit, which means I got to subtract 1 unit from x. And it was also moved down 6 units from the origin, so I need to subtract 6 onto the end. And write the interval of x values in which we're on this x squared curve. Well, -1, open circle, so parenthesis, to +3, open circle, so a parenthesis there as well. The next function we get to in order would be the square root function. Well, we've already identified the starting point for that square root function, so I'm going to pre-make my square root. We move that starting point away from the origin by moving it to the right 7 units, so x minus 7, and moved it up 6, so plus 6 on the end. Now, the square root function should have looked like this, but to make it look the way that we did with the starting point, we had to do a double reflection, so I got to make it negative on the outside, which would have turned it down like that, and then negative on the inside, which would then move it in the direction we needed. And so the domain in which we're on that square root function, we start at 3, close circle, bracket, and we go to 7, open circle, parenthesis. And the last function that we have is that horizontal line. It's at y equals 1, so we just write a 1 in here. The leftmost x value in which we're on this horizontal line is at x equals 7, close circle, so bracket. Rightmost x value is at 10, close circle, bracket.